now we are going to discuss about the remaining types of scheduling. So in the previous video, we have discussed about the first come first serve and shortest job first scheduling algorithm. So now we are going to discuss about the round robin scheduling algorithm. So so the round robin scheduling algorithm is also called as RR. Okay, it is similar to the round robin scheduling algorithm. It is similar to first come first serve scheduling algorithm, but here we have added the preemption. Okay, preemption is added. Okay, and here we have a each process has been allocated to a processor for a small unit of time. Okay, so that amount of time, small unit of time, is also called as a time quantum or time slice. For every small unit of time, the new process has been allocated to a CPU. Okay, so consider here you consider that ready queue as a circular queue. So every particular small unit of time, the processor get the new process from that circular queue, circular ready queue. Okay, so here we have a small unit of time, okay, called as time quantum, which is also called as time slice. In normally it will be to 10 to 100 millisecond length. The time second is in normal real time system. Okay, now we see the problem in the round robin scheduling. Consider the list of process and its burst time. So here we have a process P1. The burst time of that process P1 is 24. Process P2, the execution time of that process P2 is 3. P3 is also 3. Okay, so here we have a the time quantum is fixed as 4 millisecond. Okay, now let's go with the chart, Gantt chart. Okay, first, so every 4 millisecond the new task has been, the task has been shifted. Okay, so 0 to 4, the P1. The P1, as the P1 arrives first, we have allocated the CPU to the C1 first. So it executes up to 4. So the remaining time might be 20. Okay, now the P2 has been allocated. Even though the size of the time quantum is 4 millisecond, the execution time of the P2 is 3 millisecond. So it completes its execution at 7th millisecond. Then the next process has been allocated. So now the P3, the PP gets the CPU. So the PT complete its execution at 10th millisecond. Okay, now the remaining execution time for P3 is also 0. So after that, the P1 will start its execution. So for even though after every 4 millisecond, it has been, new process has to be, the processor has to be shifted to another process. But there is no other process. The P1 will keep the execution. So again, so 14, then up to 18. So 14 it will be 6, then now it will be 12. So again P1 it is 22, now it will be 8. So 2 more times less needed. So P1 again it will be up to 26. Next time slice will be up to 30. Okay, now the average waiting time the average waiting time is equal to, so the waiting time of P1 is equal to 10 minus 4. Already it has been executed for 4 milliseconds. So 10 minus 4 plus P2 ku it is 4, and for P3 4 for P2, P3 it is 7 divided by 3. So total it is 17 divided by 3. So it is equal to 5.66 millisecond. So this is about round robin scheduling. The next scheduling algorithm is priority scheduling. So here the priority scheduling, it won't consider that arrival time, all those things. The job which has the highest priority, that will be allocated to a CPU first. Now consider the list of process, burst time. So here all we need one more parameter, that is priority. So the process P1, so the burst time is 10 with the priority is 3. There is a process P2, so the burst time is 1, the priority is also 1. The P3, the burst time is 2, the priority is 4. For process P4, the burst time is 1, the priority is 5. For P5, the burst time is 5, the priority is 2. Okay, now we go for the Gantt chart. Which process having the highest priority? So P2. The P2 is having the highest priority, so it will be allocated to a CPU first. The execution time of that P2 is only 1 millisecond. It completes its work. Okay, the next highest priority job is P5. The execution time of that P5 is 5. So 1 plus 5 up to 6, it will be allocated to a CPU. After P5, the P1 having the highest priority, the execution time of P1 is 10. So 10 milliseconds, 6 plus 10, it takes up to 16 milliseconds. After that, after P1, the highest priority job is the process is P3. The execution time of P3 is 2. So it is like 16 plus 2, 18. Then the next priority task is and last one is P4. The execution time of P4 is 1. So up to 18 plus 1, 19 millisecond. So the task which having the highest priority will get the CPU first. So now we calculate the average waiting time. So the average waiting time of P1 is 6, P2 is 0, P3 is 16, P4 is 18, P5 is 1. Sorry, 1. So number of tasks is 5. So totally it is 8.2 millisecond. Okay. The problem in the priority scheduling is, see here, consider this. There are 100 process. Okay. So the process 1 having the priority 100. Okay. Before we complete the execution of all the 99 process, there are new processes are coming. So the new process priority is higher than the P1. So the P1 is never getting the chance to execute, or it never getting the CPU. That is called as infinite blocking. A particular process, due to a slow priority, it's not able to allocate it to a CPU. So it keep on waiting in the ready queue. That is called as infinite blocking. So what is the solution for that infinite blocking? So we go for a aging. For example, you consider There are four processes. At first, the priority is for this process 4 might be. Okay. So every time or every millisecond or every time the process has been allocated, the, the priority of the process, each process is getting reduced by 1 or some number you need to define. That okay. So every time we are keep on reducing the priority. That is called as aging. Okay, the solution for that infinite blocking is aging. So at some point of time, definitely the low priority task also get CPU by reducing its by improving its priority. Okay. Next one, round robin scheduling with round robin with priority scheduling. So here in the round robin, you also need to consider we have added the priority. Okay, now consider that set of tasks process burst time. So process P1 burst time is 4, priority is 3. For process P2, the burst time is 5, priority is 2. For process P3, the burst time is 8, the priority is 2. P4, it is 7, 1. For P5, 3 and 3. Okay. So and you, for round robin we need the time quantum. So that is equal to 2 millisecond. So every 2 millisecond the new process has to be scheduled. Okay. But depends on the priority. If this process having the same priority, then you need to consider the time quantum. If the process having the higher priority, it should not consider the time quantum. The highest weightage will be given to the high priority task. So we draw the Gantt chart. So the P4 is the highest priority task. So it will start its execution. The execution time is 7. So 0 to 7. Next, now the P4 has been over. Next is P2 and P3. So for every 2 millisecond it will be executed. So P2 first start, it stop at 9, then P3 11, then P2 up to 13 it come. Then P3 so up to 15. So the P2 execution time is 3. So the remaining time after it will be 1. So only 1 millisecond is pending. So it will be executed for only 1 millisecond up to 16. So that also over here it will be 6. 4 only over 2 more is there. Then so it having the highest priority, the P3 then compared to P1 and P5, the P3 complete its execution to it occupy the CPU for 20 millisecond. Okay. Then so P2 and P5 over, P1 and P5 are there. So first P1 gets so up to 22 millisecond it will execute. So remaining is 2. Now P5 get the P5 is for 24. So the remaining one now P1 gets it will execute up to 26. Again P5 will get it will execute up to 27. Okay, so this is what round robin scheduling with priority scheduling. First, the weightage will be given for even though it is a round robin, highest priority task will complete its execution. Then only the lowest priority task will get the CPU. When the round robin works here means if two processes having the same priority, there is a round robin between or among those equal priority process. Otherwise, the first highest weightage will be given to a priority scheduling, then round robin. Thank you.